In this third lecture from Chapter 7, we get to the heart of statistical inference. We will introduce sampling distribution. This lecture will be a little longer than most to ensure that we explain the concept sufficiently. This diagram is a reminder of the process of statistical inference. We take a simple random sample from the population. The sample data will provide a value for some sample statistic, let's say the mean, which then we use to make inference about the population mean. The sampling distribution of the sample mean, x bar, is the probability distribution of all possible values of the sample means. Remember in the last lecture, we noted that if we take multiple random samples from a population, we're going to get different values of the sample statistics, for example, the sample mean, and that these different sample means are not likely to equal the population mean. The key to our ability to make statistical inference about a population mean from a sampling mean is this: the expected value of the distribution of all sample means is equal to the population mean. Let's remember that throughout this lecture. We need to define the key values involved. If we look at the distribution of sample means, called the sampling distribution of the means, we know that this distribution mean is equal to the population mean, and the standard deviation of this sampling distribution, termed sigma sub x bar, is called the standard error of the mean. This standard deviation of the sampling distribution, also called the standard error, has a different calculation depending on whether the population is infinite or finite. Here you can see the ratio which determines if a population is finite. If it is, we need to use this correction factor, the square root of capital N minus n divided by capital N minus 1. If the population is considered infinite or nearly infinite, then the formula for this standard deviation of the sampling distribution of the mean, sigma sub x bar, is equal to the population standard deviation sigma divided by the square root of the sample size n. Now, to describe this sampling distribution of the means, when the population is normal, the sampling distribution is also normal for any sample size. When we are not sure of the population distribution, we can still assume sampling distribution of the means is normal for sample sizes of 30 or more. Now we have an important and useful property of the sampling distribution of the mean. We can use it to make an estimate of how close the sample mean x bar is to the population mean mu. Now I want everybody to try and remember this central limit theorem. The sampling distribution of sample means can be approximated by a normal distribution as the sample size becomes large. A normal distribution. Keep in mind what we learned in Chapter 6. If we have a normal distribution, we can use the standard normal or z distribution to easily calculate the probability in any interval. That's the heart of this concept of sampling distribution. Let's go back to our example of college admissions data. If we took a number of samples from the 900 applications and calculated those sample means, we would have this sampling distribution of the means. And if sample sizes were large enough, let's say 30 or more, we will assume that this distribution is normal and its mean is equal to the population mean of 1697. And we can calculate the standard deviation of this sampling distribution, sigma sub x bar, also called the standard error of the mean. We calculate it to be 15.96. Remember, from chapter 6, if we have a normal distribution and we know the mean and the standard deviation, as we do here, we can use the standard normal z distribution to begin easily calculating probabilities for different intervals. So based on this sampling distribution of the mean in the previous slide, let's find the probability that a random sample of 30 applications will have a mean within plus or minus 10 of the population mean of 1697. In other words, between 1687 and 1707. We can represent those two x values, 1607 or 1687 and 1707, using their corresponding z values and determine the probability in that interval. So the z value for the upper limit is 0.63. The area under the curve to the left of that from the table is 0.735. You see how we would find that from the z distribution table. And for our upper limit, from this diagram, we can see that the area under the curve to the left of that value, that z value is 0.7357. For the lower limit of 1697, we find an area or probability of 0.2643 from the z-score, as we see in this diagram. Therefore, the area or the probability between those two limits, 1687 and 1707, will be 0.4714 or 47%. Therefore, the probability that the sample mean of SAT scores will be between those two values is 47%. That's shown in this diagram. This should be a reminder that it is useful when solving normal distribution problems to always sketch or draw your distribution, the means, the standard deviation, and the x value of interest to remind you what probabilities we are searching for. If you remember the formula for the standard deviation of the sampling distribution of the means, also called the standard error of the mean, you will note that the numerator is the square root of the sample size n. Therefore, as sample size increases, the standard error will decrease. So using our example, if we increase our sample size from 30 to 100, what happens to the standard error? You can see that it decreases from 15.96 to 8.2. Therefore, our sampling distribution of the mean gets narrower with a larger sample size. And when the standard error gets smaller, the interval from 1697 to 1707 will represent a larger percentage of the total area of the distribution. From these calculations, you will see that the probability of the sample mean being in that interval increases from 47% to nearly 78%, as shown in this normal curve.